Okay, everyone. So the last one we have to think about is thermal effects on axial deformation. Like we've done this, we have, but we're going to make it explicit. So we already know what the thermal strain is. Oh, come on, I didn't want you to go forward. The thermal strain is caused by a change in temperature. We have our thermal coefficient of expansion, we have the change in temperature, we get thermal strain. But we need to now include this in our calculations for deformation. Our deformation equation before just had it based on the force. Now we're going to add in that thermal one because that's important. That's going to change things. You could be putting something in tension and cooling it and have it not move. The strains stay the same. So, with that in mind, let's try this out. Okay. So what we have right here is a high density polyethylene. And it is 120 KSI for its modular elasticity and a coefficient of thermal expansion of 78 times 10 to the negative 6 per degrees Fahrenheit. Now it's positioned in a fixture as shown. It's got a 0.1 inch gap at the top. It's 32 inches long. And it's got an area of cross-sectional area of 2 inches by 2 inches. Now at room temperature we have this gap, but what's going to happen if we start heating things up? So what we want to know is the normal stress caused by a temperature increase of 100 degrees Fahrenheit. Temperature dating doesn't cause any thermal stress. Well, it will once we reach that wall right there. I want to know the normal strain in the block at the increased temperature. Spoiler, that's actually really easy. Okay, so now if the polyethylene block were completely free to elongate, a temperature range of 100 degrees Fahrenheit would cause an elongation of 0.25 inches. This is just our thermal coefficient expansion, our temperature, and our length. This we got from beforehand. If you're wondering about this, like where's the force length over elasticity times area, where's the flee? It's because the force is 0. There is no force right now. But there's an issue with it expanding this much. It hit the wall. It hit the ceiling at 0.1 inches. So 0.15 inches of this expansion never happened. So this is another one where we can't solve just using our equilibrium equations. We would have to bring in something else. So let's bring in our force temperature deformation relationship. We know what this is. We know what this is. So we got to figure out the difference from here. So because it can only move 0.1 inches, that's deformation. And we already know what the part of that is. So if we want to, since we're trying to solve for the stress, we'll go ahead and switch it from here to here, where we replace force over area with the stress. Now, at 100 degrees Fahrenheit, we knew what one of these was. It was 0.25 inches. And so what should be happening is that this is going to cause more or less a negative 0.15 inch deformation in the other direction. So if we plug everything into our equation, we solve for the stress, what we'll get is that for it to do that, that ceiling has to be pressing down on the block with a pressure of 561 psi, compressing it. Now it doesn't like that. It's very unhappy with that, but it'll live with it. Now what's the strain in the block at this increased temperature? Now here's where it's super easy. It was only able to stretch 0.1 inches. In fact, as long as the ceiling stays constant, this is going to be the same strain no matter what the temperature is. It's just going to keep on staying the same because it can't grow anymore in that direction. Now, if we looked at it from the side, things might be different, but we're only caring about the longitudinal strain here, longitudinal strain. And that is simply the elongation over my initial length. Okay, so that problem wasn't too terrible. Just remember that we had to add that new term into our flee equation to account for our thermal strain. And so this part right here is going to be necessary. And this is how we're going to find thermal stress. So I think that's it. Yes, it is. So thank you all for listening. I hope you don't mind this kind of crazy change to our setup, but it will go back to normal quite soon. And I hope you have an absolutely wonderful day. Bye-bye.